Turkey. I'll make my presentation concise and professional as possible. So today, I will talk about analytic gradient of EFMO charge transfer energy. So from past 4 days of presentation, we've seen various methods and then platforms to calculate large molecules such as protein and novel materials. It shows how important it is to predict interactions in large chemical systems. Then how do we calculate large molecular system efficiently and accurately? The common but challenging approach is a high-level QM calculation using fragmentation method. As we talk about the legacy scientific software here, Games has been putting a lot of effort to develop effective, accurate, and computationally efficient fragmentation methods such as FMO, EFP, and EFMO. The development of fragmentation method in Games has played a very important role towards massive parallel computing, and then it is suitable for the massive parallel computing capability as well, since each fragment can be computed essentially independently of every other fragment. So this means that the computational bottleneck reduces from the entire molecular system to the largest fragment itself. So first, I'll go over the background of FMO. The FMO method was first released in Games in 2004. FMO is a QM method that is capable of evaluating the properties of a large molecular system by fragmenting in 2 ways. First, covalently bonded molecules are divided into fragment pieces so as not to destroy the bond electron pairs. And then second, molecule itself can be a fragment as a whole. FMO can do 2-body and 3-body interaction energy calculations, and analytic gradient is also available along with the other ab initio method in Games. The largest system computed with FMO is FMO2 DFTB with Games, which has about 1.2 10 to the 6 atoms reported by Dr. Nishimoto and then Dr. Fedorov. The conside of the FMO is that SCF procedure has to be evaluated for individual fragments until all the fragments are converged. This sometimes makes the gradient calculation very difficult and inexpensive. The second fragment method is EFP. The EFP was originally designed for the treatment of solvent effect on chemical reactions, but it has more recently been used to study clusters of solvent molecules and environmental effect in biomolecular systems, and then highly charged systems like ionic liquid. The unique aspect of EFP is that it uses rigid fragment, which are frozen molecular orbitals. And then, so lastly, the EFMO uses fragmentation scheme of FMO and then ab initio force field EFP method. Now the rigid body system that was in EFP should be considered as a flexible body system and then still account for the long range and short range interaction and in many body terms. Moreover, as transitioning to exascale computing involves multi-grain, massive, and flexible parallelization of the code, adoption of the accelerators, and use of bandwidth and the memory structures and so on, the EFMO method becomes very adaptable to exascale computing. While I take more of a theory-oriented role, there are brilliant members in our group who dedicate themselves working on exascale computing, a code for the FMO and EFMO specifically. So EFMO energy expression is a combination of the gas phase ab initio terms and the EFP interaction energy terms. So from the point of view of FMO, the importance of the EFMO method is the best appreciated in the context of FMO separated dimer approximation. And as a criteria for the separated dimers, there are 2 parameters that we have to take account. The first one is a user-defined cutoff value, which is R cut, and then the minimum distance between 2 fragments. So if the minimum distance is smaller than the user-defined value R cut, then the energy is calculated by ab initio terms. But if the minimum distance between the the fragment is larger, then the interaction is calculated by EFP method. So moving on to the gradient derivation of the EFMO, most of terms for the EFMO gradient is derived and implemented by Dr. Colin Bertoni in Argonne National Lab, but charge transfer energy term is not implemented yet. So from here, charge transfer by definition is the overlap of occupied orbitals in fragment A to the virtual orbital of fragment B. And it's a pairwise action, so vice versa also works as well. So as a strategy for EFM or charge transfer gradient, we have to examine each term separately, which terms can be reused from EFP, because all the EFM or charge transfer gradient starts from EFP charge transfer energy expression. The important thing about charge transfer gradient is that it's using canonical orbitals instead of localized orbitals in an occupied area or occupied space. So all the terms are derived in terms of canonical orbitals. So this is a general derivation of EFM or charge transfer gradient. And as I mentioned, the energy term is starting from the EFP charge transfer energy. And as it's a pairwise reaction, it's a charge transfer energy from A to B, and then charge transfer energy to B to A. And then all these blue terms are actually derived. Well, before that, we take the derivative of EFP charge transfer energy, and then all the blue color terms are the ones that can be saved and reused from EFP charge transfer energy gradient. And then we have to focus on the derivative terms. So MO coefficient derivative terms are now expressed as response matrix. And here, the reusable terms, which are non-response terms, are summed up and then saved in Lagrangian matrices. And then now we have all the response terms, and then this can be solved by Kapil-Pochorda-Hartree-Fogg method or the vector method. And as I mentioned multiple times, it is a pairwise interaction. So charge transfer gradient from fragment A to B, B to A are all summed up at the end of the gradient calculations. So as a computational scheme, first we calculate the RHF energy in orbitals, and then we move on to make EFP part, which is necessary for generating all the parameters that we need for doing EFP. And then we calculate multiple moments polarizability, and then we move on to EFP many body polarization. And from there, we also save non-response and response terms from there. Then we move on to dimer calculation. So if the distance between two fragments are greater than the user input value, as I mentioned earlier, we move on to EFP energy calculation. And if it is smaller, then we move on to the ab initio calculation. So in dimer EFP energy calculation, first we calculate the Coulomb dispersion and exchange repulsion energy and gradient first, because these terms are actually using LMOs for occupied orbitals. So we calculate the response terms and non-response terms separate, and then save each terms in the appropriate matrix. And then we move on to calculate the overlap. So if two fragments overlap is greater than 0.05, then we calculate the EFP charge transfer energy and then its gradient. So from there, also response term, non-response terms are separated. And then we move on to calculating the EFMO charge transfer gradient using CMO. And then at the end of the calculation, the log file will show all the EFP energies and the EFMO gradient as well. So the code is still in process of progress of implementation. And then as it is finished, it will go through all the systematic testings before public release. And right now I'm working on the increase of accuracy for total EFMO gradient. Also, large virtual orbital space, since we are using canonical orbitals, is a bottleneck sometimes to calculate the accurate charge transfer energy. So, and then gradient. So we can consider implementing balanced virtual orbitals for the virtual space in future if it is necessary. So please look forward to it. So that's short, concise, and I think I expressed pretty much everything that's important. So thank you again for Dr. Gordon, and then the committee members for this great opportunity, and then all Gordon Group members, especially the former members as well, like Dr. Colin Bertoni in our Oregon National Lab, Dr. Peng Su, Wu Pam, and Dr. Mike Schmidt. So thank you, and then any questions?